Let's consider another aspect of cycles. When we studied gas power cycles, we assumed that the working fluid was just air, and the air never changed, right? It was always air when it was exhausted. It wasn't even exhausted, right? It was cooled down at constant volume in the Otto cycle and in the diesel cycle. It was heated up at constant volume in the Otto cycle, heated up at constant pressure in the diesel cycle, but it was always air. Air was the working fluid. But you know that with real engine, what happens is that gasoline and air go into the cylinder. And hopefully the gasoline is atomized or, well, even better yet, evaporated. But there's not much of it anyway, right? It's 14 parts roughly air to 1 part of fuel. It was not too bad to say it was air, but could we do any better, especially once the gasoline is burned and we're at even higher temperatures? The exhaust gases, for example. Could we model the exhaust gases better than what we did before, where we just assumed it was all air? Because we would have combustion products. There would be carbon dioxide, there would be water, there would be a mixture of gases. And what we'd like to do is somehow come up with properties of those gas mixtures so that we could analyze our cycles more precisely. And there's many other applications for gas mixtures. One application is very common, is essentially humidity, where you have a decent amount of water in the air and the amount of water changes, right? Now water can be a little bit difficult because when it's water in the air, that water can liquefy out, and so you've got a phase change. But often we're interested in mixtures where there are no phase changes. Before we can discuss this, though, we need to clarify some concepts that, if you're like me, you probably didn't understand very well when you went through chemistry. So we're going to talk about mass and moles and fractions and what all this is. So I think that visualizing matter will help us in this case. So just look at the picture and pretend with me that this is a mixture of gases where the various sizes of these steel balls represent the various molecular weight atoms, okay, whether they're molecules or atoms, whatever they happen to be. And they're zipping around in the gas phase. We're mainly going to talk about gas here, although some of these principles apply to liquids. We're usually applying this to gases. And in fact, if we invoke ideal gas laws, for example, then we obviously are dealing with gases. In fact, we're going to restrict ourselves to ideal gases, although the chapter in the book talks about real gases. It's a little bit beyond what we want to do in the course. So just looking at this, you see that there's a couple of fairly large steel balls. There's an intermediate size. It appears to be 3 of those. It's hard to tell the exact sizes of these, but they go down to very small. There may be a handful of different sizes here. Now this is analogous to, say, a mixture of air, for example, where you have some water in the air, you have some nitrogen, you have some oxygen, and perhaps some other trace gases. They're all going to have different weights, different masses, in other words. And so there's 2 ways to look at matter. One way is to count how many of atoms or molecules you have, and the other is to just weigh it. How much mass are we talking about? So this picture is hopefully getting the right idea in your mind, but I'm going to go with a little bit simpler picture. So here's a picture where we can easily determine how many balls there are of various sizes. There are only 3 separate sizes. There's a large, a medium, and a small. And so we'll start making a little spreadsheet to keep track of all this. So we'll have small, medium, and large, and then we'll also be interested in several of the totals that we come up with here. If we count these, it's pretty simple. We could count the large ones. There are 5 large ones. They're in the outer ring. The smallest ones are in the center. There are no small ones in the outer ring. There are 7 in the center, so 7 smalls. And if you count the ones in between, the medium-sized ones, you'll find that there are 5 of those as well, just as there are 5 of the large. Now, this is analogous to talking about moles, because moles are just about counting numbers of atoms. That's really what it is. And so the equation that I'm showing you here is actually for moles, where it says if you've got a mixture of a gas and you want to know how many molecules are in it, just count all the individual molecules and add them up. Just like here, all I've got to do is count, well, there's 7 small, 5 medium, and 5 large. Add them all up, there are 17 different balls here, right? 17 different, whether it's a molecule or an atom. Usually things don't exist by themselves unreacted, except for things like the noble gases. So if we're talking about nitrogen or oxygen, then each one of these balls represents a diatomic molecule. But the idea is still the same. We're just counting atoms. Now, there are a lot of atoms in even a very small sample of mass. But this is something we could theoretically do, right? Is we could count how many of each, how many oxygen. Say we take a box of air and we just count all the nitrogen atoms or nitrogen molecules, and we count all of the oxygen molecules, and whatever's left, add counts for those. We could, in theory, count all of the, whether it be monatomic or diatomic or whatever the case may be, we could count all of those molecules in the box. And that's what moles are all about. The problem is that there's so many it becomes difficult to count. We'll talk about that in a minute. So Nm is what we call the number of the mixture. It's the mole number, right? It's how many moles there are of the mixture. Ni is the number of moles of each individual species. Like I said, in air, oxygen, nitrogen, and water. Now we could talk about percentages, or what's called fractions, mole fractions. Now before, we've used a y and an x as a mass fraction. Unfortunately, we've got to redefine it now. So in the context of the Rankine cycle, when I write a y, what I mean is a mass fraction. But now, in this chapter, when you see the symbol y, we're talking about a mole fraction, not a mass fraction. And it's pretty easy. I mean, if you want to know the fraction of the count, how many, what percentage of this count is, say, oxygen, well, that's the number of oxygen atoms over the number of the total mixture, right? That's all. It's simple. And I've calculated here. You can grab your calculator and verify if you want. I didn't pick nice round numbers. I picked a picture that was easy, and I didn't have to, search too long for it. The concept's the same, right? So if we want to know what percentage the small balls make up of the overall number of balls we've got in the picture, it's just 7 divided by 17. Now that comes out irrational. It's 0.411765. I rounded it off. Same thing with the medium and the large, right? So these are mole fractions, and they're just counts. It's a ratio of the count of the number of one species over the count of the total that's in the mixture. Maybe we've got a jar of air or something, like the 2-liter bottle we used that we pumped up full of air. As we were adding air into the bottle, what happens is we're just pushing more and more molecules of nitrogen and oxygen and trace gases into that 2-liter bottle. Now, a side effect of all this is that really these are just percentages, right? They have to add up to 100%. In other words, these fractions have to add up to 1. So if I just did this in Excel, I took that whole column, that y sub I column, the mole fraction, and just added it all up, and of course I got 1. So not really a surprise. So these three equations should make sense. We're just dealing with counts and ratios of counts, that's all. I think where students get confused is we call them moles, and then it becomes very confusing after that, but I've got something for you here in just a minute. Now, one way we like to talk about things is in terms of mass. Now, if you look at this picture, you can see why it shows it, because it's pretty obvious that the big ones have more mass, right? In fact, I don't want to think of it, don't go this way where you're thinking, well, we're thinking about the mass of one individual ball. That's not what I mean. If I took all of the large balls out and weighed them and figured out their mass, that's the mass I'm talking about. M sub I is the mass of all of one type of molecule or atom or whatever the case may be. Like if I have a 2-liter full of air and I can somehow separate out all the oxygen atoms and I weigh them, find out their mass, that's what I'm talking about when I say M sub I. That would be the mass of oxygen itself, not the mass of the mixture. Obviously there are more diatomic molecules like nitrogen in there and other things as well. I'm sure there's some carbon dioxide and water if we just take air from outdoors. But we could talk about the mass that each of those groups contribute to the overall mixture. So the mass of the mixture it's simple. It's just the sum of the masses, or the contribution to mass, of all the individual species: the oxygen, the nitrogen, the water, the carbon dioxide, if we're talking about regular air. So when you see this mass down here, the mass of 1 for the small seventh, I'm not talking about the mass of one ball, I'm talking about the mass of all 7. And I just eyeballed the picture and tried to come out with numbers that would make the example a little bit easier to digest. Okay, so I'm assuming that all 7 of these have a mass of 1. If I took them off and put them on a scale, they have a mass of 1 in whatever units I'm measuring them in. In the same way, I assumed that the medium ones would have a mass of about 2, and then the large ones, even though there are only 5, there aren't as many as, say, the smaller ones, I assumed that they would have a mass of 5. So if you think about the contribution to mass that each of these make, even though the large balls are not the majority, they contribute the majority of the mass. So if we add up all the mass, which is what this equation says, the mass of the mixture is just 8, because 1 plus 2 plus 5 is 8. Again, I haven't put any units here. So it doesn't matter if we're talking pounds mass, kilograms, whatever other mass unit you want to use. It should be apparent that all these together make up the weight of the sample, or the mixture. And there's nothing magical about putting them together. I like to talk to my daughter about living life and things, and one of the things we've been doing is doing a lot of walking on trails. And as we walk, we drink water, because we like to walk, at least 2 miles, sometimes 3 or 4. And a lot of people worry about their weight, and they don't understand it really, and so there are fad diets that come and go. And I hope that thermodynamics has convinced you that really it's just energy input versus energy output. But I was talking to her, and we both bought Camel Packs. Now, Camel Packs were popular for a while. I haven't seen much of them, but I really like it because it's just basically this small, it's not a backpack, but it's kind of like a backpack, and it's got a bladder that you fill up on the back of it that has water, and it's got a tube that comes out, and you can just drink as you walk, and it's really handy. So we both got one, and we were drinking some water, and I said, you think about it, how much weight do you gain when you drink water? And she was saying, well, none, Daddy, because it has no calories. And I said, well, yeah, that's true. Ultimately, it'll pass through you. But don't you think your weight would change? If you stood on a scale, wouldn't the weight of your body change? And she agreed that it would. And I said, well, what if you stood on the scale with your Camel Pack on and you took a drink? Then would your mass change? Well, obviously it wouldn't, right? Of course, she's in grade school. She didn't know for sure, and so it was a teachable moment. And she learned something. She said, actually, yeah, that makes sense. The mass doesn't change even though it's inside my body now, right? It doesn't really matter where it's at. If it's all being supported by a scale, then the scale is going to read the total mass. Hey, you know that, but it's helpful to be reminded sometimes of things you know. Now, we can talk about a mass fraction instead of a mole fraction. So we're going to use mf sub I for the mass fraction of the ith component. In other words, whichever species you want to talk about. Let's go back to air as an example and talk about, nitrogen, oxygen, some water vapor, and probably some carbon dioxide in it. Okay, 4 different species, whereas here, of course, we have 3 in our example. And really, the mass fraction is just what fraction of the mass does one species contribute to the overall. So it's just the mass of the ith species, for example, oxygen, divided by the mass of the mixture. Now, remember, the mass of the mixture is going to include the mass of the oxygen, so this is just a percentage on a mass basis instead of a percentage on a count or a mole basis, right? Obviously, again, these are percentages. If you add them all up, you're going to get 1, so no surprise there. Both y sub I and mf sub I sum to 1. Now, when we were talking about the Rankine cycle, what I'm calling mf now was actually x or y before. So I'm sorry for the confusion, but there it is. So we can see here that the large balls make up 62.5% of the total mass, whereas the small balls are only 1/8 of the mass. And of course, I'm assuming numbers for this because I haven't actually measured these balls. Now, some other interesting things can be done, but now we need to talk about molecular weight. Now, usually m sub w is used or mw itself is used for molecular weight. Unfortunately, in this chapter, the author does not. He simply uses a capital M. So this is going to get confusing because we've got lowercase m for mass, uppercase M for the molecular weight, and subscripts of M. Now, the subscripts of M mean mixture, the capital M means molecular weight, and the lowercase m that's not a subscript means mass. So I'm sorry, I don't make this up to torture you. I try to point out when there are very confusing things, and I think this is one of them. Molecular weight is actually a pretty simple concept, but we'll pause on it for just a second. Really, if we want to talk about the molecular weight of one species, you can go and look it up in the periodic table, right? I mean, if you look up the molecular weight of oxygen, it's a diatomic molecule, so you add the molecular weight of 2 oxygen atoms together, and there's, pretty close to the, in fact, almost, I don't know if there's a difference, actually. I think it would be exact. I was wondering if there was any effect, but I don't know. I assume it would just be, the sum of the molecular weight of two oxygen atoms would give you the molecular weight of an oxygen molecule where the two are bonded together. So if it doesn't give exactly, it'd be pretty doggone close. So what about the molecular weight of the mixture? Well, the mixture doesn't really have a molecular weight, right? Because it's the individual constituents that have molecular weights, but there could be an apparent molecular weight, because the idea behind molecular weight is just, how much mass are we talking about for a count of so many, and that so many is moles. Now, if you stick with me here, because if you were confused about moles when you went through chemistry like I was, I've got something that I think will help you a lot. They like to talk about dozens when they talk about moles, but put that out of your mind. That never helped me. I think I've got something that will help you more. So if we want to talk about the molecular, or what I should call the apparent molecular weight of the mixture, we just need the total mass of the mixture divided by the total count, the number of the mixture in moles, rather than, of course, it wouldn't be raw counts, because this would be an extremely small number, since if n was just counts of atoms, it would be terribly large. Now, it turns out that we can actually calculate the molecular weight just as a weighted average of the constituents that make up the mixture. In fact, we have to use the mole fraction, not the mass fraction, because it has to do with counts, right? So if you take y sub I m sub I, so the mole fraction y for oxygen times the molecular weight of the diatomic oxygen, and then add that to the mass fraction of the next times the molecular weight of the next, and so forth, add it all up, that will give you the average molecular weight. It's just a weighted average, really, is all it is. So it's simple. Now, you can do the same thing with the mass fraction, but in that case what you have to do is take 1 over the sum of the ratio of all the individual mass fractions over the molecular weight of those mass fractions. If you think about the units for a minute, this does make sense, but I'll leave that to you. And by the way, y sub I is dimensionless. So the units make sense. We end up with the same units as molecular weight. Now, usually molecular weight is talked about in SI units, and so it would be, grams per gram mole or kilograms per kilogram mole, whichever you like. But you could talk about pounds mass per pound mole. That's a thing. Okay, so what else could we do with this? Well, there's actually a relationship between the mass fraction and the mole fraction, and it has to do with molecular weight. So all you really do is you take the mole fraction of one species times its own molecular weight and divide by the molecular weight of the mixture, and that will calculate then the mass fraction from the mole fraction. Of course, you can rearrange it any way you like and come out with the mole fraction as a function of the mass fraction if you wish. Now, I want to show you this equation because really it's more the definition, if you will, of molecular weight. And what I've got written here is mass equals the number of moles times molecular weight. And really, if you were to rearrange it, you could simply say that the molecular weight is the mass of the sample divided by the number of moles. Now, here's what always confused me in chemistry. It doesn't matter what gas you take. It can be oxygen, it can be carbon dioxide, it can be whatever you want it to be. If you take the mass, or better yet, let's do it this way. If you take the mass and divide it by the molecular weight, you will always get the same number in of moles. And that just confused me like crazy. But molecular weight is really just how much mass there is for a certain count. And of course, you probably know I've been dancing around one word and haven't used it yet, Avogadros number, right? Well, you may not know this, but Avogadro did not come up with Avogadros number. He came up with the concept or the idea of moles. And it turns out that Avogadros number wasn't his actual number, it was in different units, but it was calculated by Johann Lochschmidt, I believe, is how you say his name. You can see his picture. But the person who gave Avogadro's number and his constant its name is actually Jean-Baptiste, I believe you say Perrin. I murdered the name, I'm sure. I don't know how you pronounce it properly. He was French. But that's where you get the number from, 6.023 times 10 to the 23rd. Now, maybe you remember this number, maybe it sounds familiar from chemistry class, and you've always wondered, well, what the heck is this thing? And you've probably been told, well, think of it as a dozen. Well, this is a lot bigger than a dozen. Let's not think of it as a dozen. Let's think about it in terms that might be familiar to you today. How about trillions, right? I mean, I find it ironic, I guess. I got to say this. I find it ironic that I can get a hard drive now rated in terabytes, right? That's how much it can hold. It has to be measured in terabytes, and our government is spending money in the trillions of dollars. They match, so that's kind of sad, but that's the way things are right now. So, but here's the thing. So if you think about trillions of things, right? Is it convenient to talk about even a million, $1,000,000, for example, to say $1 million? No, it's much better just to say $1 million, right? So it's an amount that we all understand. And of course, millions are fairly easy to understand. Billions are just 1,000 millions, right? So 9 zeros. Trillions are 1,000,000 millions, so it's a total of 12 zeros. And we're not even close to Avogadros number yet, because every time we add an exponent, we're multiplying by 10, right? This is growing just ridiculously large. And so 6.023 times 10 to the 23rd is a number that I think is hard to wrap your head around because it is so big. I think also it's hard to remember because of the 6.023. But you probably recognize that number. So I don't want you to think about it as 6.023 times 10 to the 23rd. Turns out that doesn't really matter. It's just a certain number of things. And it's, by the way, it's a heck of a lot of them, right? So if you want to say Avogadros number, fine. If you want to say a heck of a lot of them, atoms, we could define that as a unit, right? Kind of like saying a trillion or a billion or a million, when we just don't want to say a bunch of zeros and a number with it, perhaps. So really, it's just counts. That's all it is. It's how many of these molecules we're talking about. And as soon as you have a decent sized sample where you can measure its mass with, regular scale, you're talking about a whole lot of atoms. So really all we're doing is playing with counts of things and ratios of counts, and we're playing with masses of things and ratios of masses. That's all we're really doing here. Nothing more or less. Now, turning our attention to a little bit different idea, we'll talk about Dalton's Law first. And Dalton's Law simply states that for an ideal gas, the total pressure of a mixture is just the sum of the partial pressures of all the constituents in the gas. Now, the partial pressures will depend on the temperature and volume of the whole mixture, right? But the total pressure will just be a sum of the pressure contributions from all of the different species. And this makes sense because if we're talking about air that's bouncing around a room or a container, obviously as it bounces around it's applying pressure, right? That's where pressure comes from. But at least in a container. But that pressure, if say you had all oxygen in there and no nitrogen, you just somehow teleported all the nitrogen out, the pressure would be just whatever the oxygen can generate. But with the nitrogen, then the pressure is whatever the oxygen is generating plus whatever the nitrogen is generating. Now this is based on an ideal gas, but many gases can be treated as ideal. Now we can take this a little bit farther and say, well, wait a second. Each of those individual pressures divided by the total pressure could be represented as an ideal gas law ratio, right? So both are ideal gases, both the individual thing and the mixture. So we could simply write the ideal gas law for the pressure. Whether it's the pressure of the species, the partial pressure that species is generating, or if we're talking about the pressure of the mixture, you see. Now, you can go through the details here. Notice that I'm using the universal gas constant, and of course I'm using numbers of moles of the ith species, so maybe oxygen, for example, and Nm, the number of moles of the mixture. But we can still write an ideal gas law for each one of these two pressures. And you'll notice that everything cancels out except for the number of moles. And so the partial pressure of an individual species divided by the total pressure of the mixture is always equal to, at least for an ideal gas law, the count ratio, right? The molar ratio of the individual species to the total moles of the of the mixture of the species. Now, Avogadros' law, and I'm sorry, I don't know how to pronounce it. I probably got it wrong, but his law is a little bit different. It says that the volume of a mixture depends on just the addition of the individual volumes, and I just noticed I've got a mistake here. I put Tm and Vm, I was copying and pasting. It should be Tm and Pm, the temperature of the mixture and the pressure of the mixture. So I apologize for that. Let's Vm there. I'll fix it before I upload the slides and you see them. But the idea is that the total volume is really just taken up by all the individual species. So each one contributes some volume to the total volume that is occupied. So we can write the ideal gas law for these two volumes as well, since we're dealing with ideal gases. Now in the equations here I've got it correct. So you can recognize the ideal gas law, nRT over P would be equal to V, because PV equals nRT. And so it turns out that here also everything cancels except for the number of moles. And so Avogadros law and Dalton's law really yield the same idea, that either the volume, individual volume to total volume ratio, or the individual pressure to total pressure ratio, both will yield the mole fraction. As a matter of fact, we could write it this way: Pi over Pm is the same thing as Vi over Vm, and it's the same thing as the number of the ith species over the number of total elements, or I shouldn't say elements, I should say molecules or atoms in the mixture, and there's simply the mole fraction. So this is good to know. Now, this will be very useful as we solve some problems. And I know all of this seems theoretical, and we're really just dealing with counts and fairly simple ideas that make sense, but applying them can be a little bit tricky. So I've got some examples and things for you to help you understand this and work with it. Now, we don't just care about how much mass there is in a gas that's a mixture, or how many moles there are in it. We want properties, right? We want to understand the properties of those gases. In fact, if we have combustion gases that consist of a whole bunch of carbon dioxide, a whole lot of nitrogen, maybe some unspent oxygen, and some water vapor, it'd be nice to model that combustion, or not that combustion, but that exhaust gas a little more precisely so that we could make better calculations for our engines. So what we're going to do here is consider the various properties of a mixture and try to figure out how to come up with the properties of the mixture itself based on the individual properties. Now, it should be pretty apparent that if we're talking about the internal energy of a mixture, really each component of the gas contributes some energy, right? Each component of the gas has a certain amount of internal energy U. So to get the total energy, all we have to do is add up all of the internal energies of each of the species, U sub I. Now, we can, of course, write the total internal energy of a particular species, U sub I, as the product of the mass of that species, M sub I, times the specific internal energy, U sub I. But we could also write it in terms of the number of moles of that species multiplied by its molar energy, right, instead of its per unit mass specific energy. We can do the same thing with enthalpy. It's the same game, same thing. Each atom or molecule in a flowing stream will have enthalpy, and of course we just have to add up the enthalpy contributed by each of the ith species. When we can write this in terms of mass, we can write it in terms of moles. That's what the M sub I, H sub I, and N sub I, H sub I with the bar above it have to say. By the way, that bar above just indicates that the denominator is not mass. The denominator is moles, or say kilomoles. We can do the same thing with entropy. So even though entropy is an emergent property, it's still a property of the gas. And so we can certainly write the same sort of idea here, that entropy is contributed by all of the various species. We're not usually interested in the raw properties themselves. We're interested in changes. And so we could write this equation for two different states of a mixture of gases and take the difference between them and talk about changes in internal energy. Basically, all we're really doing is taking the equation and putting a delta in front of all the terms, assuming that the mass in the system doesn't change, of course. And so the delta is on the amount of energy per mass or per mole. We can do the same thing for enthalpy, and we can do the same thing for entropy. So again, these are fairly simple ideas. It's just the idea that there's an additive property, or additive, what would be the right word? I can't think of it right now. There's a mathematical name where you can just add, linear addition, I guess. It's a linear system. So that's how we could calculate changes in properties of ideal gases when it's a mixture of gases and we can't deal with them independently. Really, we kind of are dealing with them independently, because we're really just saying the whole is simply the sum of the parts. That's all we've said so far. Now, the specific internal energy of the mixture, U sub m, could be calculated based on the contributions of each of the individual species, and just a weighted average based on the mass fraction, you see. So mf sub I is the mass fraction of the ith species. It's the percentage, if you will, in terms of mass of that species. And all we're really doing is taking the internal energy on a per unit mass basis and just calculating a weighted average. That's all we're really doing here. So we can do the same thing in terms of moles, but then we have to use the molar percentage instead, Y sub I, rather than the mass percentage. We can do the same thing for enthalpy, entropy. We can even do this for heat capacities, C sub V and C sub P, where we're trying to get the heat capacities of a mixture. And of course then we could take K, the ratio of heat capacities, as Cp over Cv, and have an effective constant K, the ratio of heat capacities, for the mixture. Now of course with these we can also talk about a per mole basis or per mass basis. Either way would work. Now we're also interested in entropy changes, and so this is a little different than what we had before, where we just took the entropy difference and we subtracted it out. This has to do with some of the analysis we performed before, and you can reference back to the chapter. I don't remember the chapter number right off, but these equations should look fairly recognizable to you. Of course, the only difference is that we've got a subscript I, so we're talking about the change in entropy of the ith species, you see. And so all we really need is, well, what you see there. Now, the S naught equations are a little more precise than the others, because the others, where there's a tilde, an approximate sign, are assuming a constant heat capacity over the temperature change range. And remember, the S naughts are not really entropy properties, they're properties that depend on temperature. But then the R sub I would be the gas constant for the ith species, whether it's, as I've been using so far, oxygen or carbon dioxide, whatever it is. And then P sub I is the partial pressure of the I species in state 2, whereas P sub I 1 is the partial pressure of that species in state 1. Remember, we're talking about a change in entropy between two states, state 1 and state 2. And this is the change in entropy for just the ith species. So we can calculate it with the first equation, or we can use an approximate equation, the second one, that involves heat capacity and the temperatures in the two states. Or we could talk about both of these on a per unit mole basis instead of a per unit mass. So the first two equations are per unit mass, and the second two equations are per unit mole. Now notice that in the second two equations we're using the universal gas constant, 8.314 kilojoules per kilogram per Kelvin, if I remember right. Okay, I've got it stuck in my head, the 314, because those are the first three numbers of pi, and the 8 is fairly easy to remember for some reason. So 8.314 is stuck in my head, right or wrong, I'm pretty sure it's right. But we're using the universal gas constant, which can be handy. I prefer to deal on a mass basis if possible. Sometimes you have to go into moles, and of course in this chapter we'll use moles a lot more than we have in the bulk of the rest of the course.